Good morning, all of you. I hope all your energies and enthusiasms are growing. And today I'm going to continue. I spoke about two pillars of lattice field theories, and that was the Feynman path integral and Euclideanization. Okay. Now, there are several questions you can ask about Euclideanization. Yesterday at tea time, somebody asked, what about resonances, poles that are, on second Riemann sheet or whatever, When we were students, the searching for poles on higher Riemann sheets was so frustrating that it was one reason many of us didn't pursue S-matrix theory, okay? But it's an exact result as far as Osterwalder-Schroeder is concerned. So, of course, it doesn't mean it's easy, okay? But if you look at things carefully, you should be able to get everything of the Minkowski theory from the Euclidean theory. S-matrix is the observable content of field theories, and that full S-matrix, all its poles, branch cuts, whatever horror you have, should all be coded in the Euclidean Green's function. But as I said, it may not be that easy. In fact, this whole Weightman project of axiomatic field theory, even to this day, it has not been demonstrated for anything other than free field theory. Okay, but that doesn't mean people stopped. They went on with standard model QCD, and we have these wonderful success stories of high precision and beautiful phenomena. Okay, so axiomatic should be taken, with a pinch of salt, but they're very important because they tell you directions that you should not be following. So today I come to the third ingredient, which is called discretization. Mike Kreutz and me have a little joke which we keep sharing, and we say the continuum field theories do it without control. Actually continuum field theories don't even exist, whereas we lattice field theories do it very discreetly. Okay, so is it my phone? But why is it coming there? Okay, sorry. In fact, only it should come through my hearing aid, but every morning, I have to set this hearing aid. It's like a pilot in a cockpit. I have to check that the Bluetooth connection is fine and all the levels are okay and so on. And now this, if Bluetooth was working, you should not have heard it. Okay. Today, let's talk about discretization. As the name suggests, you take something continuous and replace it with a discrete approximation, with a way of controlling this approximation in such a way that you can get closer and closer to the continuum in a controlled way. That's the important thing. Okay. So lattice is really a way of regularizing theories, and the lattice and the spacing, they have no intrinsic physical significance. Unlike in condensed matter, where you have a given lattice spacing, it's all physical, you can't mess around with that. But here there is a way of regularizing. You have a lot of freedom about what kind of lattices you can choose and what to do with the lattice space. So let's carry on. So I come to discretization. So what does this consist of? Very simple. He takes the continuum space-time and replaces with a discrete set of points first. Which discrete set of points? You're completely free. For example, if you were discretizing two-dimensional space, this is all Euclidean space by now. We have finished with Euclideanization. So it's Euclidean manifolds. You can do it in many ways, okay? Square lattice, triangular lattice, hexagonal lattices, all of them are fine. You can even throw points randomly. It's called the random lattice, and it's very attractive in many ways, but hard to deal with. You have to be a very good person, to think in terms of randomness. All these are possible. If you take a rectangular lattice, which is the simplest, the spacing doesn't have to be the same in every direction. So you have total freedom as to how you choose these discrete set of points to approximate your continuum space-time. And this is called a lattice. Even mathematicians use the same language, so we should feel proud that at least in some respects we can keep company with mathematicians, not always, For example, one of our prime concerns is to prove confinement, and if you talk to any lattice gauge theory, they say, look, it's fairly clear that confinement has been shown. Analytically, we are not able to show confinement yet. The Clay Mathematics Institute, CMI, there's one CMI in Chennai also, but this is a different CMI. They have a $1 million prize for anybody that can prove confinement. But no physicist should waste time trying to apply to CMI to get this $1 million, because no matter what we do, mathematicians will never accept it as proof. They always find some epsilon delta to screw you, so forget about it. If for your own pleasure you think you have shown confinement on the lattice, that's fine. In fact, lattice evidence is beautiful, But a man like Atiyah, he didn't like lattice. He says, by making discretizing, you're losing a lot of topology, all these nice features of continuum, etc. But continuum may not even exist. So, and it's not true that you lose all topological information. There are some very nice investigations in lattice about the topology of gauge fields. And so discretization, is an emotional issue. But somehow, it's hard to believe that anything is really continuous in nature, all the way down, okay? So, at some point, maybe everything is discrete and everything is countable. There are no infinities. Infinities are mathematicians' way of just leading us astray, So, these are some wild thoughts about continuum versus discreteness. As I said, lattice can be freely chosen. Many times we choose this and its analogues in 3 dimensions, 4 dimensions. 3 dimensions is fine, you can visualize. 4 dimensions gets a bit harder, but at one point I was working with the 4-dimensional hypercube, and I worked on it so much that I could actually visualize 4-dimensional hypercubes, I don't know whether that was a good sign or a bad sign mentally, but So it's a matter of getting used to it. But 5 dimensions, forget it. Then what do? You had a continuum field theory with fields living at points. So you can continue to put those fields on these discrete points, fine. But the continuum theory had derivatives in it, and you have to do something about that. And the obvious thing to do is to replace derivatives by finite differences. Okay? And that's what most people do. Let's take a very, very simple theory. My capital D is space-time. So we are in capital D equal to 4. Small d equal to 3. You may wonder why I am wasting breath saying such simple things, but often this leads to confusion because people don't follow the same convention, and when you are rapidly flipping from one paper to another in the middle of the night trying to prepare for your talk in the morning, then these little differences can just lead you astray. So I consider, now, how simple can I get? D equal to 1. Can't get any simpler than that. Let's not worry about fractal dimensions and all those monstrosities. What does D equal to 1 mean? One of them is time. So there is no real space, and this is just quantum mechanics, okay, of a single degree of freedom. But we are pretending as if it is quantum field theory. No problem. Actually, you can make quantum mechanics look very much like quantum field theory. If we do that, we will start with a Euclidean action which looks like the action for a massive scalar field theory. There is only one derivative possible, and that is dx, because we are capital D equal to 1, and we take this very simple Euclidean action. What will I take? The lattice, some one-dimensional line with some points on it. Again, you can choose the points whichever way you want. You can take a random collection of points or something that, has some pattern but not uniform. But we want to keep life simple because I want you to appreciate the concepts. So we'll take uniformly spaced points with spacing A, which is called the lattice space. So we have a set of n points, and they are some integer times the lattice spacing. N can go from minus infinity to plus infinity, including 0, but often it is useful to take finite volume because you can have pathologies with infinite volume. So in that case, this n goes from minus capital N to plus capital N. These are not very important for our purpose. Now we have to replace all derivatives by finite differences in such a way that as the lattice spacing becomes smaller and smaller, approaching 0, these finite differences approach the derivative. It's elementary. High school children will be able to tell you how to do that. And there are again many choices. You can take this kind of a difference or that kind of a difference or an infinitely many possibilities. Each one of them, each choice of the lattice and each choice of replacement of the finite of the derivative leads to a different lattice action. So you can ask, my God, what have we done? We had one nice theory and you are now giving me infinity of lattice theories. Which one should I take? Be rest assured, it doesn't matter. Y is a more complicated thing, and it is not strictly proven, but everybody believes in it. In every field, people believe in some mantras, and in lattice, the mantra is, it doesn't matter which one you choose. And later, when I talk about the continuum limit, I'll try to tell you why people believe this is a reasonable thing to do. So let's take the simplest one. Okay? And it's very easy to see that derivative squared becomes this and the mass term becomes that, where I've used the notation phi n to be the field at the point xn. Now the Euclidean action h bar is many times set equal to 1. We will also do that, but you have to be careful. If you put as you progress in your life, you start putting c equal to 1, h bar equal to 1, capital G equal to 1, etc., etc. And in nuclear physics, people even put mass of the pion equal to 1. And once this famous nuclear physicist was giving a talk, and somebody asked, how come none of your results depend on the pion mass? And he himself was very confused. Later it turned out that he had set m equal to 1. Okay. So you have to be a bit watchful of what all you set equal to 1. As Bob Dylan says, you can fool some people some of the time, all people some of the time, but you can't fool all people all of the time. Okay? So shouldn't set everything to 1. Then the answer will also be 1. Fine. So you get this. Euclidean action is dimensionless. So you get this. Now you see that mass has mass dimension 1. A is a distance, so it has mass dimension minus 1. And phi has mass dimension, which I'll come to in a moment. And you can scale everything in appropriate powers of lattice spacing, make them dimensionless. So mass in lattice units is m times A. The mass dimension of a scalar field in D is d minus 2 over 2. That's why bosonic fields in 4 dimension have mass dimension equal to 1, and in 3 dimension they have mass dimension half, and in 2 dimension problematic they have mass dimension 0, and in our 1 dimensional example they have mass dimension minus half. So you scale, ml is ma, phi l is phi into a to the minus half, and the lattice action looks beautifully simple. It's very easy to verify that from my previous expression. This is what you get. Now I'll keep dropping this L because by now we know we are in the lattice, and also typing it becomes very cumbersome. So from now onwards, everything is referred to the lattice version. Now the path integral is this measure e to the minus s L, and that consists of 2 types of terms. Those that are square of the field at the point, you get a contribution from here, you get a contribution from there, and then those that couple fields at different points. So you get this. Of course, I already told you, this partition function by itself is a number, it doesn't have any information. You really should be computing the generating functional. That's all is understood by now. Now you notice that this looks very much like, oh sorry, I should have, no, okay, fine. This looks like the spin model, Heisenberg spin chain, spin at one point, coupling to spin at a neighboring point, except that our spins are phi's which take continuous values. It's a one-dimensional version of that. But this is just a partition function in classical statistical mechanics in 1 dimension. Okay. Very important point to remember. We established this for this rather trivial example, but this result is generic. All quantum field theories in capital D space-time dimensions are exactly mappable to a problem in classical statistical mechanics in capital D spatial dimensions. It's a very, very deep mapping, and it's beautiful, it's very powerful, and that is the main strength of lattice gauge theories. Okay? When we come to fermions, of course, you have to always be a bit careful. Now, because of this mapping, it allows a whole body of powerful techniques from classical statistical mechanics. Classical statistical mechanics has been around for a very, very long time, and there are some extremely powerful analytical methods of bounding free energies, sum rules, correlation inequalities, so on and so on and so forth. And you can bodily take those and apply to quantum field theory. Okay? So, what started off as, not very serious game, now has delivered us through various miracles. Euclideanization was very important for that. This mapping. So again, you should, I don't know how to, did any of you check whether our library has Zeiler's book? Probably not. Zeiler's book is wonderful because he very develops this in great detail, applies to various cases. Some of the pioneers in this area of using statistical mechanics to get deep results for quantum field theory are Erhard Zeiler, Jürgen Fröhlich, and others. Okay? So that's the most important message we have got from discretization. For example, in a abelian Higgs model, there is a phase which is Higgs phase, another phase which is the Coulomb phase. Is there a phase boundary between them? It's a physical question, right? This can be established through these kind of techniques. So let's go on. That was scalar field. But nature somehow seems to taunt us because of the first fields that we have discovered which are relevant for physics are gauge fields, electromagnets. Okay? Now, electromagnetism is very complicated in its structure. It's a theory with constraints and and so on and so on. Scalar field, which is so nice, we don't have any elementary scalars. Higgs most likely is not an elementary scalar. So let's understand how this discretization will work for gauge theories, and I will first consider abelian gauge theories. Electromagnetism. Yeah.
How did you make the comment that Higgs is probably not
That's okay. How did you make the comment that Higgs is? How did you make the comment that Higgs is probably not an elementary scalar? On what basis?
What comment?
You just said that Higgs is probably not an elementary scalar.
Yeah.
What was the reason?
I said, did you hear me properly?
Yeah.
I said, most likely it's not an elementary scalar. And there were several reasons. Actually, there are fundamental reasons why fundamental scalars are bad. So, not just Higgs, any scalar field. Now, you may or you may not take these things seriously. And so, why is Higgs suspect as an elementary scalar field? If you take 5 to the 4th theory and study it non-perturbatively, it's trivial. You may write down your Feynman diagrams and compute, etc. But if you do non-perturbatively, you find S matrix becomes 1. This has been established on the lattice also. So in your standard model, when you put your Higgs field and think it is non-trivial, it's a trivial theory. So people say that's okay. Standard model is only an effective theory. There are no fundamental scalars. This Higgs, which looks like a scalar, will get resolved into some constituent bound state later on. It is in that sense I said that. The only way to prove that Higgs is an elementary scalar is you have to probe Higgs interactions at the highest possible energies and show that it behaves like an elementary scalar. If you think you have a proof that Higgs is a scalar, that's big news, and I think you should advertise that. Okay, so let's come to abelian gauge theories, which is Maxwell's electromagnetism. And we will do it in capital D equal to 4. And the continuum action is just the Maxwell action. A is a vector potential, F is the field strength. And this is invariant under a gauge transformation, which is of this type. Now we will Euclideanize it. And remember our recipe, x naught goes to minus ix4, and A lower naught becomes plus IA4, and then you get a Euclidean action which is square integrated over all volume, and it's obviously positive, semi-definite, as we already advertised for Euclidean actions in yesterday's talk. The original action was invariant under this. Now we need to discretize. You have to discretize both the action and the gauge transformation. In the scalar field case, we didn't have this complication. We just had an action, we discretized it, and everything was fine. But now we have to find a discrete form of the action and gauge transformations in such a way that the discrete action is invariant exactly under the discrete gauge transformation. Okay. So we introduce something called a forward derivative. Okay. It's actually a forward difference. In order to get a derivative, you must divide it by the lattice spacing. Now we can discretize the field strength in this form. It's one of the possible discretizations. I'm at the moment working only with hypercubic lattice. Okay. So this is along one of the 4 directions of the lattice. What about gauge transformations? One straightforward choice is A goes to A plus 1 over the forward difference instead of the derivative divided by A. Now it's an elementary exercise that this discrete form of action, which is this discrete F mu nu squared, is exactly invariant under this discrete gauge transformation. Good. Sometimes you find that your first round doesn't work and then you have to spend a few more months, years, depending on your ingenuity, and this is how supergravity was discovered. That was not discretization. They would write down an action, and then they find that the transformations would not leave it invariant. Then they twiddle both the action and the transformation, go on and on and on, and the original discoverers had to go to, symbolic manipulation. There was no Mathematica at that time, and there was a version discovered by Tini Weltman, who got the Nobel Prize for proving renormalizability of gauge theories, called Skonskip, So they had to use that, etc. It becomes very tedious. So if in the very first round you find that you get a pair that works, that's absolutely wonderful. So we stop there. Now again, we have all the dimensional quantities like the field strength, etc. And we make them dimensionless in exactly the same way as before. Then the discretized field strength is this. You have to, by the way, no, this is the discretized field strength, correct. And discretized potential looks like that. And that is the gauge transformation. And the lattice gauge theory action is just the product of Lebesgue measures over the gauge fields, e to the minus, this should be 1/4 here, minus f mu square. So this is one possible way of discretizing abelian gauge theories. But soon we'll come across another way of doing it, which is dramatically different, and its physics is very different, and wait till we come to that. You can also call it Lie algebra discretization, because the fields are the elements of Lie algebra. Later we will find a group discretization where the elements are group elements. Okay? It's also called non-compact, and I'll come to why it is called non-compact. Now there is a problem here, because different configurations, namely values of A at different points, differing by gauge transformations give the same contribution, and there are infinitely many of them. So this path integral is divergent. It is not well defined, even though we did all this rigmarole for that. And that's the complication with gauge theories. And one way of fixing this is so-called gauge fixing. So this theory, even on the lattice, in order to make sense, you will have to fix the gauge. Now we turn to non-abelian gauge theories, which is an area which is so central to our understanding of particle physics today. Okay? And they were introduced by Yang and Mills, and they're called non-abelian because there is an underlying non-abelian group associated with these fields. We will consider so-called compact Lie groups. Okay? So these are Lie groups whose group volume, in a sense to be made clear shortly, is finite. In my abelian case, the gauge transformation parameter was lambda, and that went from minus infinity to plus infinity. So the group volume is infinity. That's why it's called non-compact. But non-abelian gauge theories, the gauge volume at least is compact. Okay. So we'll look at groups like SUN or UN because they seem to be most interesting to us. Dimension of the group is denoted by dim G. Technically speaking, this is the size of the adjoint representation of the group. If you take SU2, the adjoint representation is 3-dimensional. If you take SU3, adjoint representation is 8-dimensional. And the size of the adjoint representation is called the dimension of the group. Now, there are as many vector potentials as the dimension of the group. In the abelian case, we had only one. Now, if it is SU2 gauge theory, we'll have 3. If it is SU3 gauge theory, we'll have 8. 8 gluon fields and so on. So we have to give a little group label to the vector potentials. Some little bit of mathematical details. The generators of the group are taken to be Hermitian, and here there is a split between the mathematics community and the physics community. We tend to choose the generators to be Hermitian, and the mathematicians tend to choose the generators to be anti-Hermitian. Okay? So you have to keep that in mind. It doesn't really matter. It's a matter of convention. They satisfy the Lie algebra, and then normalization, because this is a nonlinear relation, you have to, it admits only specific normalizations. If I scale all A by certain amount, the Lie algebra will not hold. Okay. So the normalization one chooses is this. You look at these generators in the fundamental representation of the group. So for SU2, it's the two-dimensional representation. SU3, it is a three-dimensional representation. In that representation, each generator is represented by a matrix. So in the fundamental representation of SU2, these are the 2 by 2 Pauli matrices, and you can take it to be, and in SU3, there are, 8 of them, 3-dimensional. So you normalize it like this. FABC are called the structure constants of the Lie algebra, and a lot of properties of the Lie algebra and group theory can be understood in terms of the structure constants. They are very important. So far this is just mathematics. We have not invoked anything that is specific to physics. Now it is convenient, instead of working with this vector field with a space-time index as well as a group index, to consider what is called the Lie algebra valued vector potential. You just contract them with the generators. Many of the formalism becomes compact, but whenever a formalism becomes compact, it is actually a lot of complications hidden in. It's like differential forms, okay? It all looks very beautiful, but if you have some doubt, then you have to go back to your component formulation and work it all out, okay? So it is nice and elegant for those who are already used to it, and those who are not used to it, it can be as confusing as any other approach. But we will follow the Lie algebra valued approach because, I like it. Now the non-abelian gauge transformation looks like this. Now the gauge parameters are group elements. At each site, you associate an element of the group. This is the analog of the capital lambda of the abelian gauge thing. Now you can also define Lie algebra valued field strength, and that is given by this form. Why did we choose such a complicated form? And that has to do with the fact that we want objects that transform nicely under gauge transformations. In the abelian case, field strengths were invariant, but in the non-abelian case, we can't quite do that for some very deep reasons. But so we look for things that transform nicely. You could have just stopped with this, but that would have transformed lousy. It's like doing general relativity in terms of things which are not tensors. Okay. Everything is a big mess. So nice transformation property is, makes life easy and makes analyzing these theories also nicely. So under this group gauge transformation, this object transforms very nicely. This inhomogeneous term, inhomogeneous because this doesn't depend upon the quantity you're looking at, is completely absent here. Field strengths in the non-abelian case not invariant under gauge transformation. But they have a nice property, and that is called covariant transformation. This is exactly what happens in general relativity also. You have many things that are not invariant but are covariant. And when things are covariant, you can do a lot of things. You can put them together, build up a big edifice out of it. So that is the important difference between abelian and non-abelian case. The significance of this will come out very soon. Now we want to discretize. This is all in the continuum. So we will play the same game as we did in the abelian case and try to discretize the field strength like this, and the gauge transformation, the derivative is simply replaced by a finite difference. At this time the algebra is more messy, you can make a lot of mistakes, and even after you have cleared all the mistakes, you find that this field strength under this discretized gauge transformation does not transform covariantly. Now that's bad news. So we will do like what the supergravity guys do. You tinker with the transformation law till you find something which is nice. But no matter what you do, as long as your field variables are the potential, there is no discretized form of gauge transformation that you will find which will lead to a covariant transformation law for the field strength. Now this is not an accident, there is a deep underlying mathematical reason for that, and this is one reason why, though we are often suspicious of mathematicians because of the epsilon delta type of approach, that we must pay attention to them because they discover certain things which are very important for us. If we didn't pay attention to the mathematicians, you know hundreds of papers will be coming on constructing discretized non-abelian gauge theory based along these principles, where mathematicians tell you, stop it, just listen to us, and it will all be magic, as we will see. So the resolution rests on a very beautiful concept in mathematics and some fundamental properties, mathematical properties of groups, connections. So what is of importance is something called holonomy. Okay. So what is holonomy? Sounds very, we are always afraid of names, and we should be, because you can just go on proliferating full of jargon. We won't cut down on jargon. We want names to be transparent, etc., etc. But holonomy is the basic minimum you can do. So what is holonomy? So U is an element of holonomy, and it is defined along a curve. The curve has a starting point, x, and an ending point, y. So there is a curve here. What you do is, you introduce something called the path-ordered exponential. I'll explain in a moment. So the path-ordered exponential of e to the I g naught a dx is what the mathematicians would call a holonomy element for the connection A. Okay? Just as we have Christoffel connections in general relativity, the gauge fields are connections. They have almost identical properties as the Christoffel connections. So what is the meaning of this? You divide the curve, which goes from x to y, into a very large number of segments. Sorry, this is small x. X1 is first segment, x1, x2 second segment, X and Y last segment, and these segments are ideally extremely large, so each one of them is infinite. Why do we do this? Because infinitesimals are easier to handle. You can prove various nice results, even though now I believe infinitesimals are in trouble because apparently there's something called Topos theory which will replace everything we learned with infinitesimals. And of course, we all admit that when we first learned integral calculus, this infinitesimal was always a bit mysterious, You have to assume a lot of things. But then you get browbeaten into thinking that it's all fine. And much later, when your life is almost about to end, then you realize that you were right. The infinitesimals are really problematic. And you should have been more courageous and attacked them when you were young. And now at least, be happy that your intuitions were correct. Now it turns out that if I take, so this is what the path order exponential is. You take the exponential, split it into these very small segments, many of them, and for each segment you write that, and you order them. Why do you order them? Because each of them involves the Lie algebra valued object, and they do not commute at different points. So the order is very important. So you just order it. And that is your holonomy. What's the big deal about it? Most amazing property is that under gauge transformations, the infinitesimal holonomies transform covariantly. Infinitesimal one, you can show this. You can just look up my book, or any book, should explain this fact. Now, if each of them transforms homogeneously, then let's see what happens to the whole thing. So this is gx1 dagger, this is gx1, gx2 dagger, but gx1 dagger from here and gx1 from there give 1, because the group element satisfies g dagger is g equal to 1, and all the transformations in between drop out, and you get that the entire holonomy transforms covariantly. So we found that our old-fashioned approach did not give us nicely transforming object, but the new search in terms of holonomies gives such objects. Now non-abelian lattice gauge theories are now going to be built based on these holonomies and not the gauge fields. Okay? Now Yang has a nice way of saying this. In the case of abelian gauge theories, the vector field gauge field is not physical because it transforms under gauge transformations, and field strengths are invariant. But in the non-abelian case, fields also transform covariantly. So there is some information in them which is useful, and the holonomies are the optimal variables for non-abelian gauge theories. Now the recipe for constructing non-abelian gauge theories on the lattice is to use holonomies along each link of the hypercubic lattice. So what do I mean by that? Let's consider a two-dimensional lattice. So here, let's say this is in the mu direction, and this is a site x. Put on this link in the forward direction a holonomy which is x, starting at x, going one lattice spacing in the direction. So you do it for all the link variables. The collection of link variables is a gauge field configuration in this way of doing it. Not the vector potential. Vector potentials have now been banished. So how does this work? And that is the task that has to be determined. Then we are able to write down the non-abelian gauge field theories on the lattice. Is that watch correct? Yeah, it is. Okay. Ah, you can switch it off. Now let me go back to this distinction between compact and non-compact. By the way, this construction works for any gauge group of the type SUN, including U1. So U1 is an abelian gauge theory, but now in this group theoretic language. So the variables are not the elements of algebra, but elements of the group. That's why some people call the first way I showed you as a Lie algebra discretization. But you can also use link variables even for the abelian theory, and that there the basic variables are group variables, not algebra variables. So in the case of abelian gauge theories, there are two choices available for putting them on the lattice, and they have different properties. Okay. So let's go back to our abelian case. The gauge fields for A mu, and A mu could take value all the way from minus infinity to plus infinity. It just could take any real value, which means the volume of the field space is infinity. Non-compact. What mathematicians mean by non-compact space is the volume is infinite. So this variable lives on a non-compact space. The gauge parameter lambda also could take values minus infinity to plus infinity, and the volume of the gauge parameter space is also infinity. So that is also non-compact. But now, in terms of the link variable formulation, the gauge parameters are group element Gx. So what is their volume? You know that in order to talk about volume, you need to have some measure on that space. If I take Cartesian coordinates, the measure is dx divided dz. If it is polar coordinates, it is r square dr, sine theta, d theta, d phi. So there is a measure involved in that. So the group elements can be parameterized, and the parameter space is a group space, and it's a manifold. It can be given a metric, it can be given a measure, and in terms of that measure you can find out what its volume is. So there is something called the Haar measure. The beauty of the Haar measure is you don't need to know what it is explicitly, ever. Okay. And you can just use its property that groups like SUN, SU3, SU2, U1, they are compact. And if you use the Haar measure, the total volume is finite, and you can normalize it So the total volume is always 1. So the Haar measure satisfies Tg equal to 1, and this of course is a finite volume, it's a compact space. Now what about the gauge fields themselves? Now the gauge fields are linked variables which are also group elements. So you can use the same Haar measure to find out the volume of the space of gauge fields, and that is also 1, which is also compact. Now these two have to be either both compact or both non-compact. You can't have one, you can't have the gauge field to be non-compact and gauge parameter to be compact, etc. And in particular, you cannot have gauge fields to be compact and gauge parameters to be non-compact, because the gauge parameters can be used to transform the gauge fields, and if that volume is infinity, the gauge fields will also have infinite volume. So this is what we mean by compact gauge theories and non-compact gauge theories. Important point is electromagnetic abelian case can be described both ways. Okay. Now the field strengths, they transform. Now I got tired of writing the group valued, Lie algebra valued function, components and so on. It transforms covariantly, which means all chains of field strengths at the same point, they will all transform covariantly. Now you take the trace of that, and these are all finite dimensional matrices. You can use cyclicity of trace. Trace A, B, C is equal to trace C, A, B. It's not true for infinite dimensional matrices. A wonderful counterexample is quantum mechanics, because if you take X and P to be represented by matrices, the Heisenberg commutation relation says xp minus px is IH cross. If cyclicity of trace were true, if you took the trace on the left side, you would get trace xp equal to trace px. So left hand side is 0, right hand side is infinity, go into a contradiction. So only for finite dimensional matrices, cyclicity of trace can be used, and that is all we need here. So all these traces are group invariants. So you can build an invariant action by taking any of these that you want. So let's look at the simplest invariant trace FF, and if you write it in terms of the object with group indices, this is the invariant Lagrangian, and this is the action for a non-abelian gauge theory written in this component formulation. But that's only one example. Now we will introduce something called Wegener-Wilson loops. Where did Mr. Wegener come? He is a, condensed matter theorist. Little bit of history for you here. Wilson formulated his lattice gauge theory in 1974. Quite before that, Wegener had formulated something, because he was looking for a generalization of the Ising model, and he wanted to write more Ising model-like objects which had certain so-called duality properties, and he came up with the simplest lattice gauge theory, where the gauge group was just the discrete group Z2. Okay? And he had everything. He had Wilson-like action, gauge transformations, all that. So Wegener should really be credited as being the first discoverer of lattice gauge theory. But that was for discrete gauge group. For continuous gauge groups, my dear friend Jan Smith. He was a graduate student in UCLA around the same time I was a postdoc, and he discovered lattice gauge theory independently of Wilson. He had worked out everything. And where he got stumped was when he started putting fermions on the lattice, and he discovered the doubling problem. At that time, he didn't know what to do about it, and he just didn't do anything. So, Wegener, Jan Smith, Wilson, they should all be credited as having discovered lattice gauge theories independently. It's important to give credits where they are due. Very few people realize actually Jan Smith had discovered lattice gauge theories as a graduate student. Okay? Wilson was very graceful and he gave full credit to Jan Smith, and in one of the conferences he made it quite explicit that Jan Smith had actually discovered lattice gauge theories. It's just a little bit of history. Now, that is the continuum, the invariants that I talked about. Now let's look at invariants of lattice gauge theories. There are many, many of them, and a very general way of constructing them is these are called Wegener-Wilson loops. Fortunately, both their names start with W, so we can call them by the single symbol W. Now, what is a Wegener-Wilson loop? Take any closed loop. On a hypercubic lattice, you can okay. So you take a closed loop supported by links, and on each link you put your link variable, and you take a product of the link variables in the same order. That is called a Wegener-Wilson loop. There is no problem if these intersect. Yet, so you have a lot of freedom in constructing these Wegener-Wilson loops. What's the big deal about the Wegener-Wilson loop? You can switch off the light. So let me take a path which is 1 to 2, 2 to 3, and then comes back because the path has to be closed. Now under gauge transformation, the first one transforms as G at 1, G at 2 dagger. This is G of 2, G of 3 dagger. So here you will get G of 2 dagger, G of 2, which is 1. So all the intermediate G's drop out, and the entire Wegener-Wilson loop transforms as G at the starting point, loop, G at the starting point, dagger. So it transforms covariantly. You see how beautiful it is. Constructing covariant objects now is almost trivial. You don't have to struggle with derivatives, covariant derivatives, and all that. Okay. And you take a trace of this, by cyclicity, you can bring G dagger to here and use G dagger G equal to 1, and the trace of all Wegener-Wilson loops is gauge invariant. So you can choose any of them or any combination of them to construct your invariant action. So now we have lots of freedom. We have a choice of lattice, which points you take, and the choice of the Wegener-Wilson loops. So again, you can construct a very large family of lattice gauge theories. A question arises, which of them is correct? And we'll try to answer that. I have to keep track of time here. Okay. Yeah, that's about it all. Now I have 7 minutes left, and let me just finish it. So we will look at something called plaquettes. Plaquette is just a French name for square. Okay? Now that is very, why should a French name be so special? Because Europeans have a weakness for anything French. Okay? Maybe we should find a Punjabi name for a square and write our books only in terms of that, or a Tamil name, because in Tamil Nadu it's very important that you don't, take Tamil lightly. I'm a Tamilian, but I keep taking Tamil lightly all the time because it's fun to tease people a little bit. Okay. So it's just a name for a square. So I take a square like this. In the mu direction, then this is in the nu direction, then I backtrack in the mu direction and come back here. So this is a U dagger, this is a U dagger. The product of those is the plaquette variable P. So U1, U2, U3 dagger, U4 dagger. Now when the lattice spacing is small, A is small, this is, there is some numerical factor which I don't remember, but you can look up any book, even my book will tell you that. Again, A to the fourth, F mu nu A square, and there are more and more and more. So now if I sum all the plaquettes, this is trace. So this is the plaquette variable, and trace of the plaquette variable at this form, trace 1 minus P. You sum over all positions of the plaquette, all orientations, and this will look like summation A to the fourth from here, F mu nu A square, and that is nothing but D4x F mu nu A square in the continuum. So the continuum Yang-Mills action can be obtained just by taking a lattice gauge theory action, which is sum of plaquettes, all possible plaquettes. Okay, so that is called a plaquette action. It's the simplest action for lattice gauge. But we saw that there are all kinds of invariants, and you can build lattice gauge theory action with any of them. But if you want in the A going to 0 limit that it should look like the continuum action, then part of it, can be from plaquette actions, part of them can be from more complicated Wegener-Wilson loops, etc., etc., etc. So now we are finally able to write down the partition function or the path integral for lattice gauge theory. And that consists of integral Haar variables. We already introduced them for every link on the lattice. So there are as many links as edges. E to the minus some parameter beta trace 1 minus placket. So this is the lattice gauge theory proposal. It is based on compact variables U and is invariant action is simplest invariant action is made out of the placket. Now what about observables of the lattice gauge theory? Observables have to be gauge invariant. So any gauge invariant object so you can have placket which senses the non-abelian fields locally For example, you put a quark on the lattice and an anti-quark on the lattice, and you want to see what is the field distribution
Haridas,
all over this place.
excuse me. You forgot the P dagger also. It's P plus P dagger.
Huh?
P plus P dagger. Placket plus placket dagger.
Yeah. Sure. Some number. Only in SU2 you don't have to worry about. Yes, thank you. So in such a case you will measure the plackets in all these places, and that is how the profile of the Yang-Mills flux tube was measured with great accuracy. But you can have non-local observables. One of them is so-called a Wilson loop. Which is very large rectangle, and these probe, for example, in the pure gauge theory, the static potential between quarks and antiquarks. And if you want to establish confinement, then the potential in the linear, the potential doesn't have to rise linearly for confinement. As long as it keeps increasing with R, it will confine. But linearly confining potentials, the potential will rise linearly, and if it acts for a time t, the energy is proportional to R, and the factor which is e to the IET, in Euclidean case becomes e to the minus ET, so you get e to the minus TR, which is the area. So one of the criterion for confinement is the expectation values of large Wilson loops should obey the area law. Okay? And then there's something called Polyakov loops, In lattice gauge theory, we almost always impose periodic boundary conditions along all directions. So now you can consider just a line instead of a square. You multiply the link variables and take a trace. Because these 2 points are identified, this is also gauge invariant, and that is called a Polyakov line. And now you can measure Polyakov line at one point, Polyakov line at another point, and look at the correlation function. And in fact, this is what we did when we investigated the Yang-Mills flux tubes here in IIMC. I had built a cluster supercomputer in 2004 for that, and that also gives the static potential. So you can go on constructing various kinds of observables, and that, is a summary of what I did yesterday and today about how lattice gauge theories are constructed, and in particular for gauge field theories, both abelian and non-abelian. Okay? So this will conclude the construction of lattice gauge theories based on the 3 pillars that I talked about: path integrals, Euclideanization, and discretization. Now in the next talk, what I'm going to do is address this question. We have so many different lattice actions now. Which is correct? If they're going to make predictions, and if they all make different predictions, then you should shut down lattice gauge theory as an activity and ask Musk to take all lattice gauge theories to Mars. But it turns out that what we want is not a gauge field theory in the lattice, but we want gauge field theory in the lattice in the limit when the lattice spacing is taken to 0. That in the continuum field theory language, because of divergences, you first regulate the theory. You use some cutoff, whatever you want, and then you renormalize. Okay? After renormalizing, there is still a cutoff dependence. This is not very clearly stated in many books. Only difference is before renormalization, the cutoff dependence is dangerously bad. After renormalization, this is much milder. So after renormalization, you can remove the cutoff in a nice and harmless way. So these are the 3 steps in continuum field theories. In lattice, it's exactly the same. So you have a cutoff, which is a lattice spacing, and then there's a lattice version of renormalization, which I will try to explain is a little bit more some subtle, and then you remove the lattice spacing. Now it turns out that since I have scaled everything with respect to lattice spacing, in the path integral, you can't see the lattice space. So how do you take it to 0? The way to take it to 0 is that coupling 1 over G naught squared, that has to be tuned with lattice spacing. And in effect, it removes the lattice spacing. And in order for a continuum limit to make sense, this lattice theory must possess a second order or higher order phase transition in the language of classical statistical mechanics, which means correlation lengths must diverge. Okay. Now the folklore in classical statistical mechanics is when you have a whole lot of theories, then they are dictated by fixed points, And many lattice theories will be governed by the behavior of few fixed points, and therefore even though you have Hamiltonians which are very, very different, their scaling behavior is the same. Okay? So the hope is that all this enormous family of lattice actions belong to the same universality. This is not proven. Even in fixed point theory, it's not rigorously proven how it happens. And already in lattice we have an example. If you take three-dimensional abelian Higgs model, you can renormalize it in two different ways. You can either keep the mass gap fixed, or you can keep the string tension fixed, and they lead to different continuum theories. Okay? So there is some subtlety about it, but by and large, we expect this universality to work, and all these different lattice theories will yield the same continuum prediction. The most surprising thing about QCD, which I will try to explain later, is that this phase transition happens when the bare coupling constant is close to 0. So you would think it's all perturbative. No. Even the non-perturbative parts of QCD can all be obtained in this limit where the bare coupling constant goes to 0, and it's a very subtle point which is worth understanding, and if time permits, I will try to explain that. So in tomorrow's lecture, I will try to explain to you what this non-trivial continuum limit of lattice gauge theories is called the, statistical continuum limit. You simply don't take A to 0. If you take simply A to 0, that's like removing the cutoff without doing renormalization in old theory, and you simply keep getting infinities back. So you have to do this lattice version of renormalization, and then you must take the lattice spacing to 0. This I am going to explain to you in terms of a d equal to 1 example that I developed. It is not realistic, but it is sufficiently illuminating. And I will use the transform matrix method which I talked about, which was important for establishing that the Euclidean Green's functions have sensible corresponding Minkowski Green's functions. Reflection positivity, which implies a positive transform matrix. So I will construct the transform matrix, examine how the continuum limit goes, what type of fixed point that simple theory has. It turns out the fixed point of that elementary example is very, very close to the fixed point of QCD, which is not first, second order, third order. It is what may be called in the Landau scheme infinite order phase transition, where there is an essential singularity in the temperature variable. It turns out that TIE example has the same kind of. So that will tell you at the same time how transform matrices work, and will also explain the statistical continuum limit of lattice gauge theories. After finishing that, I will try to spend the remaining time trying to explain whatever I can on fermions, but that's a big jungle. We will be modest about it, and whatever we can, we will. Thank you.